Okay, the purpose of this video is to demonstrate how to get the results for a two-way ANOVA using StatCrunch and writing up the results. And one thing I need to do is analysis was performed using StatCrunch. And remember, we just put the web address there. And even if you're just interested in using StatCrunch, I think it'd be really interesting for you to contrast and compare how this was done in R and how it was performed in StatCrunch, because we have some limitations in StatCrunch. It's not a high-level statistical software like R is. So there's some things we have to do a little bit differently, and some of the numbers are a little different. So first thing we'd want to do is obviously go get our data. I should have already had this done. I'm messing around. I'm going to use the systolic over BMI. So wherever this is on your machine, pop it into StatCrunch and go from there. All right, so sample size we can find easily by scrolling down. So sample size is 300. Next thing we want to do is we want to get our descriptive statistics. I feel like I shouldn't even really be showing this at this point, but let's go ahead and do it anyway. So sample size, mean, standard deviation, the median, the min, the max in Q1 and Q3. So, run these and report these for the quantitative dependent variable. So, again, report the mean and standard deviation up here. Next thing I would do is I would go to the graph, go to a box plot, do systolic, make sure that we are identifying outliers. And we can see that we have 4 outliers. You can see down here that I copy and pasted that plot under graph 1. I can see my outliers here are 164, 166, 168, and 186, which I have reported. Now, there's a limit on that. If there were 20 outliers, I would probably just report that there were approximately 20 outliers that ranged from, the low number to the high number. But since there's a manageable set of outliers, I report all of those. All right. Next thing I would do is grab a histogram of systolic, and I copy and pasted that right there. Next thing I'd want to do is I'd want to analyze my frequencies. So I would want to grab age and BMI, and I want my frequencies and relative frequencies. And you can see that I took that information and put it in this table. Also, something I like to do is I like one sentence that pulls out kind of an interesting feature of the information from a table. I don't like to just present a table and not have a narrative that pulls out at least a little bit of information. I don't want to go overboard. I'm not going to write every single thing I see here. People can glance at the table and get that information. But I like to pull something out. So what I did is I pulled out for each of the independent variables, in this case, the one with the highest count. 42%, 127 was the largest count for age, from 40 to 64. Obese was the highest count for BMI category. Yeah, I just report that. So nothing too crazy. Next thing, the two-way ANOVA was conducted to address the research question. Means and standard deviations in parentheses are presented in this table. With StatCrunch, I get that when I run the ANOVA. So let's do that. So my dependent variable would be systolic. I want age, be my category. I want to plot my interaction, I want to display the means, and I want to compute the Tukey, and I want to save my residuals. Remember, the residuals are going to be used to test the normality assumption. All right, gang, what we got? Tunnel vision on the interaction. It's not statistically significant, so our focus becomes on the two main effects. But notice right here, I have the means and counts for the cross table. I don't have the standard deviations. I'm not really even sure. I'm not even really sure how we can pull that out. Let's see. I don't think we can pull that out, the standard deviations. So, yeah, I mean, we just can't do that. So, daggone it, I wish there was a way to do that, but I just don't know any real way to pull that out. Yeah. So I guess we would delete the standard deviations. If anybody can figure that out, let me know. I don't like StatCrunch. I hide the fact. So we would need to come through, and this is going to be a pain. All right, just pretend that all these are deleted. I'll tell you what, let's just go ahead. It's not going to take that long. I got nothing better to do. It's got 14 reports and grading and grades to put in and all this stuff. So. All right, are we having fun yet? Might want to just skip ahead while I'm sitting here farting around deleting standard deviations because I can't figure out how to report those in StatCrunch. All right, so there we go. That wasn't too bad. So we do have an unbalanced design. Sample sizes are not the same in the cells. So I tell the reader that I'm going to construct that. All right. And let's go back over here and grab the let's see the result. We did the two-way ANOVA. So let's bring that up. All right, so you can see that what I do next is I concentrate on the ANOVA table. And I say that the interaction is not significant, so I reported the interaction information right there. And I have to go into R and calculate the effect size. And the main effects for BMI and age were significant, as we can see across here, the top two lines, and I report that. And again, the effect sizes come from R. You probably can get online and type in calculate effect sizes for two-way ANOVA, and there's probably some effect size calculators out there that allow you, if you're just one of these anti-R people, you can probably find that, but I'm going to turn that over to you. So the observed effect sizes for BMI were low, age was high, so I report that there. And then I come into the two-way ANOVA, which is really just taking this information absent the model line. I don't care about the model line in reporting this. Actually, I do care about the model line, but I wouldn't report it. And put that information in the table. Next thing I did is I come in with the Tukey post hoc. Notice the Tukey post hoc, first of all, gives me for age. And all three were statistically significant, so I created a table So notice the 18 to 39 to 40 to 64 comparison was significant at the 0.001 level. The lower bound was 6.06. The upper bound was 14.68, which I put in this table. Comparing 18 to 39 and 18 to 39 is irrelevant, so there's dashes there. And you can get this information up here just by the information down here. Again, comparing, 18 to 39 with 65, it's the same thing as comparing 65 to 18 to 39, so it would be the cell right here. Should go without saying, but I've learned in education, don't ever do things without saying. Now when I compare systolic blood pressure and BMI, those results are right here. And you can see that the only one that is statistically significant is the obese with the normal weight comparison. So I report that just in narrative right here. I don't create a table for it. The interaction plot, kind of cool. You get two of them, whichever one kind of turns you on. Copy and paste it. I copy and pasted this one right there. All right, so we move on to the testing the assumptions. Testing the normality assumption is kind of goofy the way that's done in StatCrunch, but we have to run this pseudo phantom t-test to get the Shapiro-Wilk normality test. So you can see we just violate the heck out of the normality test. So I report that our test statistic is 0.98. Reported, p-value is less than 0.01, reported. So we're violating the normality assumption. You have to do the, okay, where are we here? There we go. The variance, you have to do the homogeneity of variance per independent variable. So I'll have to do systolic first with age. And you can see that I've reported that in this line right here. There is a concern with equal variance assumption because we reject the null, which assumes that states that the variances are equal. But interestingly, when I run this for BMI, I don't get equal variance problems. I can't assume equal variance. So I just tell the reader that I don't like this near as much as the way that R performs these, but again, different strokes for different folks, right? That's it. All right, all I got. Take care.